Good morning. We had been looking at the single phase inverter circuit. We already looked at half bridge as well as full bridge, and we started on pulse width modulation techniques for the single phase inverter, bridge inverter particularly. So pulse width modulation technique is used mainly for two purposes. One is for controlling the RMS output of the AC voltage from the inverter. So if we are having a fixed voltage source, if we are having a square wave inverter, if the voltage source magnitude is VDC, then the output is going to be VDC as well, the RMS output. Whereas if we try to adjust the width of the pulse, the RMS value can change. That is one thing. The second one is harmonic control. So the harmonic components in the output can be controlled based on the kind of width we are adopting as well as the kind of pulse width modulation technique we are adopting. So in that sense, let us first start with single pulse modulation technique. So single pulse width modulation technique. As the name indicates, we are going to have only one pulse in the positive half cycle and one pulse in the negative half cycle. And we are going to adjust that pulse width to get variable amplitude, RMS amplitude at the output. So if we say this is the DC voltage, which is VDC, and we are going to have one switch here and one more switch here, and we have one switch here and one more switch here. So these are the four switches in the full bridge inverter, and we are having our load connected somewhat like this. So let me name the devices again. This is S1, this is S4, and this is going to be S2, and this is S3. And let me call this point as A and this point as B. And when positive half cycle is happening, we are going to have the load current which is flowing from A to B. So this is going to be positive half cycle. And when the current flows the other way around, that is B to A, this is negative half cycle. So this is going to be positive half cycle and this is going to be negative half cycle. Normally what we expect is if it is a square wave inverter, we are going to have for the complete positive half cycle, we are going to have a positive voltage. And for the negative half cycle, we are going to have a negative voltage. And this is going to repeat itself like this. So this is omega t. And this is going to be 0. This is going to be pi. And this is going to be 2 pi. This is the way we normally look at the waveform when we are having square wave inverter. And this will be plus VDC and this will be minus VDC. And what we are drawing is load voltage or VAB. This is what is VAB, a voltage across the load. If we are using single pulse width modulation technique, then we can look at it this way that if this is omega t, and let us say this is again pi, and this is going to be 2 pi. So this is pi and this is 2 pi. So we are going to fire S1 and S4 at an angle alpha. And we are going to allow it to continue to conduct until pi minus alpha. So this is going to be alpha. And this is going to be pi minus alpha. And similarly, this point where this is being fired is pi plus alpha. And this is going to be 2 pi minus alpha. And we are going to have a waveform somewhat like this. So that means we are going to fire S1 and S4 during this positive half cycle from alpha to pi minus alpha. And we are going to fire S2 and S3 during this interval. The same thing is going to continue for the next cycle as well. So what happens is there is no voltage from 0 to alpha and there is no voltage from pi minus alpha to pi. So if I try to calculate the RMS value, so if I say V load RMS value, if I try to calculate, it is going to start from alpha and it is going to go until pi minus alpha. And we have to say Vd square d omega t. And we are going to average it over pi. And we have to take the square root of this. This is going to be the RMS value. So we can take Vd out and d omega t when you integrate, it is going to be pi minus alpha. It's going to be omega t. So when you substitute the limit, it is going to be pi minus 2 alpha divided by pi. Because pi minus alpha. So this is going to be the square root of this. So this is the RMS value. So when we had alpha equal to 0, that is when we had square wave inverter. And in square wave inverter, we had output RMS value to be Vd. It was not any different because pi minus 0 divided by pi, square root of that. So that's going to be Vd. Whereas when you have a larger and larger angle alpha, then correspondingly, this RMS value is going to come down further and further. So by increasing alpha, so you can say alpha can be varied from 0 to pi by 2 at the most, because if you make it pi by 2, then the pulse width is going to be literally 0. There will not be any pulse at all. So alpha can be varied from 0 to pi by 2. So correspondingly, output voltage or output RMS value decreases or reduces. So this is going to decrease further and further as the alpha value is increased towards pi by 2. So this is for mainly amplitude control. We will look at what kind of impact it is going to have on the harmonic content eventually when we work out a problem. So the second type of pulse width modulation technique that is adopted, that is called sinusoidal pulse width modulation technique. So sinusoidal pulse width modulation technique is another technique which is very, very commonly employed in many of the inverters, UPS, because we want sinusoidal output in those cases. So sinusoidal PWM technique actually produces or generates an output waveform which emulates a sinusoid. So rather than having a square wave shape, if it can emulate a sinusoid, nothing like it. So that is the reason why sinusoidal PWM technique is adopted all the time. So in sinusoidal PWM technique, what we try to do is to compare a sinusoidal wave. So let us say this is the sinusoidal wave I am talking about. So this is generally known as the modulating wave. So this is the kind of output that we want to produce. So this is omega t. And let us say this is the kind of sinusoidal wave we are looking at. Let me probably adopt a carrier wave. So I'm going to have one sinusoidal wave and one carrier wave. And the carrier wave, what I am looking at is having a frequency which is 6 times that of sinusoid. That is the reason why I am drawing this, basically just to show that this entire cycle is divided into 6 portions. So I'm going to have the sinusoid looking somewhat like this. And let me actually extend this division to the positive side also. So this is divided 6 times. Now, when I adopt the carrier wave normally adopted is a triangular wave. So let me again take as though this is the bottom side of the triangular wave and this is the top side of the triangular wave. And the triangular wave is going to go like this. So let us say this is going to go into the peak at these points. These are the peak at these points. So it's going to, I have to draw as though this is a line. And from here, it is going to come down like this. So one cycle is over. Then this is the second cycle. I hope you get the trend of what I am drawing. So this is the kind of triangular wave I'm going to have. Now this triangular wave and the modulating sine wave, these two are compared with each other. They are going to be compared with each other. And depending upon which one is higher at any instant, we are going to get the pulses. So what we do is, there is a triangular carrier wave at higher frequency. And we are going to have sinusoidal modulating wave at the fundamental frequency. That is, whatever is the output frequency we want, that is going to be the frequency of the sinusoid we choose. Now, these two are compared with each other. So triangular wave and sine wave are compared with each other. So whenever we are going to have the triangular wave greater than sine wave, we are going to have a negative pulse, or we can say S22 and S33 are S2 and S3 are fired. So we are going to fire S2 and S3. Whereas on the other hand, if we are going to have a triangular wave smaller than, or its amplitude is smaller than sine wave, then we are going to have S1 and S4 are fired. So let's look at this itself. If we are looking at the points of intersection, this is one point of intersection, this is another point of intersection, and we are going to have 2 points of intersection here, then 2 more here, and we have again 2 more here, then we have here also 2 more, and these are 2 points at which they are intersecting, and we are going to have 1 more here. So we are going to have totally, if you look at it, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there are 12 points of intersection. And we know that if S1 and S4 are fired, it is going to be positive half cycle. So load voltage is positive. Load voltage is going to be positive here, whereas here load voltage is negative. So we are going to have load voltage to be negative. So let us try to look at this here. Let me just draw the waveform again for the output wave. So if this is omega t, you can see that at this point, this is the modulating wave is smaller as compared to the triangular wave. So we are going to have a negative voltage during this portion, whereas this is going to be positive. And similarly, from here to here, you are going to have the sinusoidal wave greater than the triangular wave. So let me name this point as O, this point as P, this point as Q, this point as R, this point as S, T, and so on. So in this particular case, this is going to be like this. And here from Q to R, there is a small negative portion. And from R to S, we are going to have actually a big positive portion. So we will have a big positive portion. And from S to T, again, we have a negative portion. So this is going to be a negative portion. So we can say these points, that is O, this is P, this is Q, this is R, this is S, this is T, and so on. So this is the kind of waveform we are going to have. So this is the load voltage what we are going to get. So if you look at it, near the peak of the sine wave, we get a wider pulse. And near the zero crossing of the sine wave, we are going to get a narrower pulse. So the pulse width or area under the pulse is going to be proportional to, it is proportional to the amplitude of the sine wave at that instant. So if I'm going to have the sinusoidal amplitude being emulated by the area under the pulse, then that is actually going to produce approximately an RMS value which is close to the sinusoidal wave itself, or the waveform itself is going to be close to sinusoid. So in this particular case, there are two important parameters for the sinusoidal PWM technique. The first one, what we talk about is the frequency ratio. So frequency ratio is ratio of the frequency of the triangular wave. So this is triangular wave frequency divided by sinusoidal wave frequency. So that is going to be really the frequency ratio. That is one of the most important parameters in this particular sinusoidal PWM technique. We said there are two parameters in the sinusoidal PWM technique. One is frequency ratio, which is actually going to be frequency of triangular wave divided by frequency of sine wave. The second one is called modulation index or amplitude modulation index. So the modulation index is whatever is the amplitude of sine wave or peak amplitude of sine wave divided by peak amplitude of triangle. So if the sine wave and the triangular wave both are having the same magnitude, then this is going to be 1. So what we drew earlier, if you may recall, what we had done was we had drawn a sinusoidal wave like this, and we had drawn a triangular wave somewhat like this. So this is the kind of triangular wave we had drawn. So if this is the triangular wave, in this particular case, the triangular wave peak is greater than the sinusoidal wave peak. So if our sinusoidal wave is even smaller, let us say if our sinusoidal wave is going to be even smaller than this, it's going to be very, very small, which means the modulation index is going to be very low. In that case, we are going to have positive pulse which is as wide as this. This is going to be the positive pulse. But negative pulse will also be pretty wide because we are having the sinusoid really much shorter as compared to the triangular wave. So what I'm trying to get at is positive pulse width will be much larger than negative pulse width during the positive half cycle of the sine wave if modulation index is close to 1. If it is going to be close to 1, then we are going to have a very good amount of RMS value because the output pulse width in the positive side will be much wider. On the other hand, if modulation index is close to 0, then we are going to have the RMS of V naught is rather it is decrease. It is going to decrease. So RMS value of V naught will decrease if modulation index is smaller and smaller. So I would say in one sense, the modulation index, which is defined as the peak amplitude of the sine wave to the ratio of the peak amplitude of the sine wave to the peak amplitude of the triangular wave, this modulation index is proportional to the RMS output from the inverter. If I have a good amount of modulation index which is close to 1, I'm going to get the RMS value to be quite high. If not, it is going to be low. Second thing I want to mention is about the frequency ratio. So in the case of frequency ratio, if I'm going to have the frequency of the triangular wave, the frequency of the triangular wave, let us say that is 6 times that of frequency of the sine wave, like what we saw, there will be an intersection which is probably going to take place 12 times. So if n is the frequency ratio, if n is the frequency ratio, 2n will be the intersection points. And if there are two n intersection points, every pulse goes from positive to negative or negative to positive during every intersection. So there will be n pulses at the output. So you can say either n positive pulse or n negative pulse. So n pulses at the output. So there will be n pulses at the output. So if I am saying that this is going to be 100 volts power supply, and here is my inverter, and this inverter is being operated on sinusoidal PWM technique, and I'm trying to look at what is the kind of output that is coming across the load. So if I look at what is VAB, I am going to have basically some pulse like this. Then I'm going to have probably a bigger pulse like this. Then I'm going to have one more pulse like this. From here, it is going to probably go into the negative side. Then I will have one more, and then I may have something like this. So I'm showing essentially this is the kind of pulse we are going to have. So in which case, we are going to see that this maximum amplitude will be 100 volts and the minimum amplitude will be minus 100 volts. So the peak of the approximated sine wave. So if I say that this is the kind of sine wave I'm going to have, and this is essentially repeating itself in the negative half cycle also, the peak of the sine wave at the most can be 100 volts. So I can't have definitely the RMS value greater than about 100 by root 2, which is 70 volts. So the maximum RMS output voltage can be only 70 volts, nothing more than that, because this is 100 by root 2 approximately. So the sinusoidal PWM technique definitely will give you much less of a voltage than whatever is the DC voltage that is available. That is the reason why in many of the UPS system, inverter system, we normally look at about 300 or 350 volts being the battery voltage if I want really 230 volts of AC, RMS. So if I want 230 volts output RMS from the UPS, then I should have 350 volts of battery voltage as far as the input is concerned. So this is really, really important. It's a very important fact because the DC bus, the battery value will be chosen accordingly in many of the UPS systems. Otherwise, at the output, you may have a transformer, which will be a step-up transformer. In many of the household applications, we may use only 24 volts or 48 volts battery. So what we get at the output of the inverter will be much less than that. We may get only 35 or 30 volts. And that has to be stepped up to 230 volts before really it is being utilized by our home inverter. So that is the reason why we should know exactly what kind of rating of the battery, voltage rating of the battery and ampere hour rating of the battery that we need to choose for a particular application. That's important. Now, another point which we have to make is about the harmonic control. So when we are looking at what kind of harmonics will be present in the output. So let us say omega t is rather omega is the fundamental frequency. So sine omega t is going to be the fundamental wave. So let us say this is sine omega t. Triangular wave now is going to be sine 6 omega t or sine 9 omega t or whatever. So this is going to be the wave, triangular waves frequency. It's not sinusoidal, but I'm just approximating. So when you actually look at these two being superposed on each other, so we are going to have sine omega t and sine 6 omega t superposed on each other. So this will be sine a plus b and sine a minus b. So we are going to have sine 7 omega t and sine 5 omega t coming up. So the lowest order harmonic that we are going to see in this particular output waveform, apart from the fundamental, is fifth and seventh. So if I'm going to have an even frequency ratio, even number frequency ratio, which is actually some n, then the lowest order harmonic present is going to be n plus or minus 1. This is going to be the lowest order harmonic present in this particular output waveform. So if the frequency ratio is 12, then we will have 11th and 13th harmonic present in the output wave, which will be the lowest order harmonic. Definitely there will be more also. There will be like 23rd, there will be multiples of all these things that will be coming up. But the lowest order harmonic, what we see will be 11th and 13th, because 12 is the frequency ratio in this particular case. Okay, so these are two major pulse width modulation techniques that are used in a square wave inverter, in a single phase inverter. So let's try to work out one problem, one numerical example. So a numerical example on single phase, single pulse width modulation technique. So let us first try to work out this problem for single phase, single pulse width modulation technique. So the problem statement is like this. A single phase inverter, a single phase full bridge inverter has an input DC voltage of 100 volts. Calculate the RMS output voltage when single pulse width modulation, single PWM technique is used with the pulse width per half cycle being 120 degrees. Calculate THD of output voltage. So this is single pulse width modulation and the pulse width is given to be 120 degrees in this particular case, which means if this is omega t and if I'm going to have this as 0, this as pi and this as 2 pi. What I have as the pulse width is 120 degrees. So I'm going to have a pulse width which is corresponding to 120 degrees like this. Okay, so this is 120 degrees. So the total is 180 degrees, out of which 60 degrees are left over as blank spaces. So this should be 30 degrees and this should also be 30 degrees. So in this particular case, alpha is equal to 30 degrees. That's what it means. And similarly, I'm going to have on the negative side also, this is 30 degrees. So this will start from 210 degrees and another 120 degrees I have to add to this. So this will become 330 degrees. So if I want RMS value, so V naught RMS in this particular case will be, you have to start from 30 degree, which is pi by 6. And you have to go until 5 pi by 6 because this is 150 degrees. And what we have got as the voltage, this is corresponding to VD. In this particular case, VD is given to be 100 volts. So I have to say VD square d omega t, and this has to be averaged over pi, and we have to take the square root of this. Okay, so in which case I have to take this as VD, and within this integration, what I have got is just omega t. So after integrating, what I'm going to get is omega t. So that omega t I can write as 5 pi by 6 minus pi by 6 divided by pi. So this is 4 pi by 6 or 2 pi by 3. So this is going to be VD multiplied by root of 2 by 3. So this comes out to be 0.8164 VD. Or I can say this is 81.64 volts. If square wave modulation technique had been adopted, I would have got complete 100 volts. Now 100 volts has been decreased to 81.64 volts. So for square wave, V naught would have been 100 volts RMS. But for alpha equal to pi by 6 or 30 degrees, what we have got as V naught RMS is now 81.64 volts. Now THD has to be calculated. So for calculating THD, we'll have to use this particular expression. So THD or total harmonic distortion will be V naught RMS square minus V1, which is the fundamental RMS square, which we will calculate using Fourier expansion. Square root of this divided by V1 RMS. So this is going to be total harmonic distortion. Now, to calculate the fundamental, so to calculate the fundamental component, what I need to do is I have to calculate, if you may recall the Fourier expansion, we have to say f of omega t as Fourier expansion will be, first of all, whatever is the DC component or average component. And we have to say sigma n equal to 1 to infinity. Sorry, not 0 to infinity, n equal to 1 to infinity. We have to have an sine n omega t plus bn cos n omega t, where we are going to write FDC is the average value of the periodic waveform, and an is equal to 1 by pi integral 0 to 2 pi f of omega t sine n omega t d omega t. And similarly, dn is equal to 1 by pi integral 0 to 2 pi f of omega t cosine n omega t d omega t. So using this, let us try to calculate, especially for this particular waveform, whatever we have drawn, let us try to calculate what is the fundamental value. So I should say A1 and B1 are the fundamental value. FDC will be 0 anyway, because positive half cycle is equal to negative half cycle. So we are not going to have any average value at all. So A1 is going to be 2 by pi, because I can just integrate from 0 to pi. That is sufficient. So 2 by pi. And only thing what I need to do is 0 to pi. But 0 to pi is not, the function is non-zero from pi by 6 to 5 pi by 6 only. So I should be able to write from, let me write this once again. So A1 is going to be 2 divided by pi. That is going to be 2 divided by pi. Integral of, the limit is from 5 pi by 6 to 5 pi by 6. And we can write this as V DC, which is 100 volts, sine omega t d omega t. And similarly, B1 is going to be, again, 2 divided by pi. Integrating limits are from pi by 6 to 5 pi by 6. And VDC cos omega t d omega t. So this is going to be 2 VDC divided by pi. This can be taken out. And for sine omega t, the integral is minus cosine. So this is going to be cos pi by 6 minus cos 5 pi by 6. So that is going to be 2 times root 3 by 2. Okay, because cos pi by 6 is root 3 by 2. On the other hand, here this is going to be 2 VDC by pi divided by multiplied by sine of 5 pi by 6 minus sine of pi by 6. And sine 5 pi by 6 and sine of pi by 6 both are equal to each other. So this is going to be 0, whereas this is going to be this 2 and this 2 can be cancelled with each other. So this is going to be 2 root 3 divided by pi VDC. What we got for the square wave was 4 VDC by pi. So for square wave, we got A1 to be 4 VDC divided by pi. This is what we got as the A1 value for square wave. Now, 2 root 3 by pi VDC happens to be the peak of the sinusoidal wave, fundamental sinusoidal wave. So I should write fundamental wave is equal to 2 root 3 divided by pi VDC sine omega t. So RMS of the fundamental is going to be, this has to be divided by root 2. This expression has to be divided by root 2. So 2 divided by root 2 is root 2. So root 6, root 3 multiplied by root 2, which is root 6 divided by pi VDC. This is going to be the RMS value of fundamental. So that corresponds to root 6 divided by pi multiplied by 100. And that comes out to be 77.97 volts. So what we wrote as total harmonic distortion is V0 RMS square, which is 81.64. So we can write THD is equal to V0 RMS square minus V1 RMS square root of this divided by V1 RMS. So this is going to be 81.64 square minus 77.97 square root of this divided by 77.97. And this comes out to be 31%. Whereas what we saw as the total harmonic distortion for a square wave. So THD for a square wave inverter happens to be 48%. This is what we calculated earlier. So definitely THD has also decreased when we reduce the amplitude of the RMS wave. So when you adjust alpha, both the amplitude and the harmonic quantities in the output both kind of get decreased. So let us try to do one more problem where we are going to say calculate the output RMS value for single pulse width modulated case of one phase bridge inverter with alpha equal to 45 degrees. So what we got was, in the previous numerical example, we had derived this. We said that this was Vd multiplied by pi minus 2 alpha divided by pi square root. This is what we had derived earlier. If alpha is a particular value, we have to substitute that here. So correspondingly here, alpha is pi by 4. So V naught RMS is going to be VDC multiplied by pi minus 2 alpha divided by pi. So if VDC is 100 volts, so I should write this as 100 multiplied by 2 alpha is pi by 2. So this is going to be pi minus pi by 2 divided by pi, square root of this. So this is going to be 100 divided by root 2, that is 70.7 volts. So we are looking at lesser and lesser magnitude of RMS value as we increase alpha further and further. For alpha equal to 30, it was 81.65 volts, whereas for alpha equal to 45, it is 70.7 volts. One more, I'm not exactly giving the numerical example, but I'm asking you to think about this derivation of current waveform for a single phase square wave inverter. So if I'm going to have a square wave inverter, a waveform somewhat like this. So let us say this is the positive half cycle. This is going to be the negative half cycle. And this is going to be again the positive half cycle. This is the way it is going. So which means it will start from some negative current value and it will keep on increasing and it will reach probably a particular value. And again, it will come down and then it will reach this value. So this is going to repeat itself. So if it is an RL load, so we are talking about current waveform for an RL load. So if I'm going to have an RL load, this is the kind of current waveform we are going to have. So if we say that this is going to be I max, this is going to be minus I max by symmetry. And if we say that this is going to be plus VDC, this is going to be minus VDC. And if this is T by 2, this is going to be T. This is the period of the inverter. So in which case, during positive half cycle, we would have had the waveform or equation to be Ri plus L di by dt equal to VDC. So for this, if I try to write the solution, we have to write I of t equal to VDC divided by R. This would have been the steady state current if we had allowed this to continue further and further, multiplied by 1 power e power minus t by tau, plus whatever is the initial current. Initial current had been minus I max. So I should write minus I max multiplied by 1 minus e power minus t by, not 1 minus, I max multiplied by e power minus t by tau. Now, it had started from I max and it would have reached plus I max when the time has elapsed to the extent of half a cycle. So I should say I of t by 2 is equal to I max and that is going to be equal to VDC divided by R multiplied by 1 minus e power minus T divided by 2 tau. And I can write again, this is minus I max multiplied by 1 e power minus T divided by 2 tau. So from here, we should be able to get what is I max value. So I can say I max multiplied by 1 plus e power minus T divided by 2 tau equal to VDC divided by R multiplied by 1 power minus T divided by 2 tau. From which I should be able to get what is I max value. So this will give us what is the maximum current that is going to be reached, and minus I max will be the minimum current that is going to be reached. So if we have what is the VDC value, what is the R value, and tau is L by R. So what is the L value? And what is the kind of frequency at which the inverter is operating? We should be able to calculate I max as VDC divided by R multiplied by 1 minus e power minus T by 2 tau divided by 1 plus e power minus T by 2 tau. So this should be able to give us what is the I max value. So if we have I max and if we have I minimum, we may be able to calculate what is the kind of RMS value. And if we have the RMS value, we should be able to calculate the power. And the power can be calculated as whatever is I square times R. So that will be I RMS square times R. That will be able to give you what is the actual value of power. So if we have the power, so power can be calculated by computing the RMS value of current. That is definitely not going to be easy because the RMS value has to be calculated in the form of 1 divided by pi integral of I square d omega t. And I itself is having exponential, so it's not going to be very easy for us to calculate this. But however, at least you should know the method how the RMS calculation is done. This has to be taken square. Of course, the current is going to be taken from 0 to pi. It has to be integrated from 0 to pi. So you can simply use the expression whatever we derived for I. So we can use this expression and it has to be integrated. So after calculating RMS current, so if I may call this as I naught RMS, then I should say I naught RMS whole square multiplied by R load. This is going to be the power delivered. So this will be the power delivered to the load. Now, what is the kind of current that is being supplied by the power supply? So current supplied from VDC will be, if I call this as capital P, so capital P divided by VDC will be IDC. So this will be the average current delivered by the DC source. Okay. So this kind of takes us to the end of single phase inverter. We will be looking at three-phase inverter subsequently in both star connected and delta connected mode of loads. Now that we have completed all the PWM techniques corresponding to single phase inverter, I'm going to migrate to three-phase inverter. And three-phase inverter is very, very commonly used, especially when we want to control the speed and torque of three-phase AC motor drives. Whenever I'm going to employ the inverter for three-phase AC motor drive speed and torque control, it has to be a three-phase inverter. So I have to have the output in the form of A, B, C phases. That means I will need three independent legs. So which means I am going to look at something like this. I have my input as VDC, but the output is going to be in the form of one leg. This is the second leg, and this is the third leg. So I'm going to have three legs like this, conducting depending upon which switch is on and which switch is off. So from here, I am going to take the loads, and the loads can be again connected in star or delta. Okay, so I'm going to number them exactly the same way like I numbered earlier. So this is A phase. Let us say this is going to be B phase and this is going to be C phase. Just like how we did in the case of rectifier, I'm going to call this as S1, this as S4, this as S3. I'm going to call this as S6, and this is going to be S5, and this is going to be S2. So I'm exactly numbering them the same way as I had numbered in the case of rectifier. And I'm going to have one load connected here, the second load connected here, and the third load connected here. And I'm showing them in star format. Please note. Okay. So let me call this as ZA, this as ZB, and let me call this as ZC, and I'm calling this as the neutral of the load. So I'm going to have this as the neutral of the load. Now from this side, from the VDC side, when I fire any of the positive device, let's say S1 I am firing. So the current would go in such a manner that the current is going like this. It will go like this. It will go through S1 and it will actually flow through ZA. But I should have a return path. Unless there is a return path, I'm not going to be able to have the current flow through this load at all. So the return has to be either through 6 or it has to be through 2. So, or it can be through both of them, for example. So I can have the current flow like this, and through 6, it will return to the negative of the supply. So this is going to be one of the ways in which I can have a current through the three-phase load. But please note, in this particular case, I'm going to have only two phases are active. That is ZA and ZB are active. The third phase is not active at all. So it could be that way. So this essentially tells us that I can have only two devices conducting at one point in time, at one instant of time, or I can have three devices conducting at one instant of time simultaneously. So I can have either two devices or three devices conducting simultaneously at any point in time. So this essentially tells us that I can have 6 and 1 or 1 and 2 or 2 and 3, then 3 and 4. Then I can have 4 and 5 and 5 and 6. And each combination would cover up for 60 degrees duration. So 6 multiplied by 60 degree, it will be 360 degree duration. So in this particular case, if you look at it, one conducts for this 60 degree and this 60 degree. Two conducts for this 60 degree and this 60 degree. So every device would conduct for 120 degrees. So this particular pattern is known as 120 degree conduction mode. When I'm going to have only two devices conducting at a time, we call this as 120 degree conduction mode. Whereas if I'm going to have three devices conducting, for example, I may have 6, 1, 2, then 1, 2, 3 and 2, 3, 4. Then 3, have I missed out something? 6, 1, 2, 1, 2, 3, then 2, 3, 4, then 3, 4, 5, then 4, 5, 6, 5, 6, 1, then again 6, 1, 2. So now if you look at 1, 1 comes up here, 1 comes up here, and 1 comes up here also. So each combination is for 60 degree. So totally we are going to have this as 180 degree conduction mode of each device. So each device is going to conduct for 180 degrees. So particularly when I was talking about single phase inverter, I talked about a particular case called square wave inverter, where you're not going to modulate the output in such a manner that it is sinusoidal, or you eliminate harmonic, or you have any amplitude control. Nothing is going to happen. So you just fire it and forget about it for 180 degrees, and you fire the other two devices for the next 180 degrees. So a similar thing, what happens in three-phase inverter is either you fire every device for 120 degrees or you fire every device for 180 degree. You are not going to modulate the output sinusoidally or in any specific manner. So I can have either 120 degree conduction mode or 180 degree conduction mode. And let's try to look at the waveform for star connected load. When I have star connected load, what happens in 120 degree conduction mode and what happens in 180 degree conduction mode. So I'm going to say three-phase inverter with star connected load. So I'm going to look at star connected load. So in star connected load, first I'm going to take up 120 degree conduction mode. So when we are looking at three-phase inverter with 120 degree conduction mode, let me again draw the circuit. So this is my three-phase inverter. I'm going to have S1, this is S4, this is S3, this is S6, and this is going to be S5, and this is going to be S2. And I'm going to connect from here. I'm going to have this as my A phase and this as my B phase and this as my C phase load. So these are going to be three three-phase loads that are connected here. So let me call this as A, this as B, and this as C, and this is going to be S1, this is going to be S4, this is S3, this is S6, this is S5, and S2. So let's say this is ZA, this is ZB, and this is ZC. And if I am talking about load phase voltage, I have to look at what is the voltage across this. That will be VA. And similarly, what is the voltage across this? That will be VC. And I'm going to always assume this will be at a higher potential compared to the neutral, because that is what we are always calculating, what is the potential of this point, that is point C with respect to neutral. So that is going to be VC. The same way I'm going to look at what is the voltage of this point A with respect to neutral. So that is going to be VA. So this is ZA. So this is what we are looking at. Okay. So when I am going to have 6 and 1 conducting, let's say initially I'm going to have 6 and 1 conducting. So this is omega t. This is also omega t. And I'm going to have initially 6 and 1 conducting. So let me draw. This is VA and this is VB. And I'm going to finally draw VAB also. Okay. So when I am having 6 and 1 on, I'm going to have this VDC being applied somewhat like this. Let me draw the equivalent circuit. So I'm going to have 1 on, and from 1 it is going to go towards ZA. Okay, so this is 1 on, S1 is on, and I'm going to have ZA conducting, and I'm going to have ZB conducting because my device number 6 is on. So this is also going to conduct, and this is the neutral. And I'm going to have S6 conducting. So this is S6, and it has arrived at the negative side. So this is VD. So entire VD is going to be divided between ZA and ZB. So this will be VD by 2, and this will also be VD by 2. So each of them are going to share, is going to share VD by 2. So if I look at what is VA, that will be positive VD by 2, and my VB is going to be minus VD by 2. Okay, so this is the way I'm going to have my voltage. So let me write this magnitude as VD by 2, and I'm going to have this also as minus VD by 2. So this is 1 conducting and this is 6 conducting. So after 6 and 1, I have to have 1 and 2. So when 1 and 2 are conducting, I am going to have actually 1 continuing like this further. But if I draw, for example, VC, if I draw what is VC, I am going to have during this portion no conduction at all across ZC in the first 60 degrees. So I will have literally 0 voltage coming up here. So this is the first 60 degrees that I am talking about. The next 60 degrees I have 1 and 2. So I will have this as the voltage, and B phase is not participating at all. So I will have 0 voltage, whereas C phase is participating. So I will have a negative voltage. Okay, so this is going to be minus VDC or minus VD by 2. Now, after this, I will have 2 and 3. When 2 and 3 are coming up, 2 will continue to conduct. So I will have minus VD by 2 coming up again. So 2 will continue. So this is due to 1 and 2, and this is due to 2 and 3. So this is again, if I try to write, this will be 6 and 1, and I should write here also 6 and 1. Now I have 2 and 3. So very clearly I am going to have after this 2 and 3 will take over. So 3 will be a positive voltage here. So this is going to be VD by 2. By then 1 is gone. So I'm going to have 0 voltage. So So I will have 0 voltage coming up. And after that, I have 3 and 4. Because 3 and 4 are coming up, I am going to have 4 is the negative device for A phase. So I will have here 3 and 4, and this is going to be the kind of waveform I have. So again 4 and 5, I'm going to have a waveform like this and so on. So this is going to repeat itself. So this will be the kind of waveform I will have for A phase, and this will be the kind of waveform I will have for B phase. Right? And this will repeat itself. The same way I will have here this coming up. So this is the kind of waveform I'm going to have. So I can very clearly say, if I just erase this, I'm going to draw this once again. Sorry. So I'm going to have 6, 1, then 1, 2, then I'm going to have 2, 3, then 3, 4, then 4, 5, and 5, 6. Then again 6, 1, 1, 2, and so on. Now you look at VAB, how much this is. So I am going to have VA minus VB as VAB. So if I try to look at when 6 and 1 are conducting, it is going to be VD by 2 minus VD by 2. That is what is going to come up. So I am going to have essentially VD coming up here. So I will have VAB as VD here. Then after that, I have, so this is when 6 and 1 are conducting. When I'm going to have 1 and 2 conducting, I have VB to be 0, whereas V1 is VD by 2. So I will have VD by 2 coming up. So this is the way it is going to be. And if I look at 2 and 3 conducting, VA is 0, whereas I'm going to have this to be 3, which is plus VD by 2. So from here it would have gone to minus value of VD by 2. Then I will have 3 and 4 conducting, which will come out to be this is minus VD by 2 because 4 is conducting and 3 is plus VD by 2. So minus VD by 2 minus VD by 2. So this will be minus VD. So I will have a waveform somewhat like this. This is going to turn up like this. So this is the kind of waveform I'm going to have for VAB. So if you look at the levels, I'm going to have this as VD, and this is going to be 0.5 VD, and this is going to be minus 0.5 VD, and this is going to be VD. Again, this is going to be VD by 2 minus of VD by 2, and so on. So if you look at it, the line voltage has 4 levels. It is going to have 4 levels. And what are the 4 levels? We are going to have 0.5 VD, and I'm going to have VD. So I have VD, 0.5 VD. Then I'm going to have minus 0.5 VD and plus VD. So line voltage has 4 levels, whereas if I look at the phase voltage, VA or something like that, VAN or VBN and all, I'm going to have 3 levels. The 3 levels are VD by 2, then 0 and minus VD by 2. These are the 3 levels. So in the star connected load configuration with 120-degree conduction mode, I have line voltage having 4 levels, whereas phase voltage having 3 levels. So this is the working corresponding to 120-degree conduction mode. Okay. Now if we try to look at again 3-phase inverter, star connected load, but let us try to look at 180-degree conduction mode. So what is the kind of inverter waveform we are going to get for 180-degree conduction mode? So let me try to again draw this inverter. So I'm going to have 1, 4, 3, 6, 5 and 2. So this is the complete configuration of the inverter, and I'm going to have 3-phase loads again connected in star. So this is one phase, this is the second phase, and this is going to be the third phase, and this is the neutral. So let us say I connect this here, and I connect this here, and I connect this here. Okay, so let me call this as 1 and 4, and this is A, and this is 3 and 6, this is B, and this is 5 and 2, and this is C. Okay. Now this is VDC, what I have here. Now let's say I'm going to take 1, 2, 3. So let me draw the waveform correspondingly. Let me draw the waveform corresponding to 1, 2, 3, 2, 3, 4 and so on. Okay, so let me first of all draw the circuit corresponding to 1, 2, 3. So I'm going to have first of all 1 is closed and 3 is also closed. So I'm going to have, this is ZB because this is 3, and I'm going to have ZA because it is 1, and both of them are connecting to the neutral, and I'm going to have here the other ZC, and this is returning through 2. So this is going to connect it like this. This is how it is connected. Okay. So if I assume that a current I is flowing here, it will obviously divide itself into 2 portions. This is going to be I by 2. This also is going to be I by 2, whereas this is going to be I. So this carries twice the current, whereas these are carrying only half the current, assuming that I'm going to have the same impedance connected, balanced impedance connected across all the 3 phases. I'm going to have here 1 by 3 VDC getting dropped, and this is 2 by 3 VDC getting dropped. So 2 by 3 VDC plus 1 by 3 VDC becomes the total VDC here. Right? That is the way the voltage is going to be. So I can draw all the 3 phases, basically, the voltage waveforms here. So this is the second phase and this is the third phase. So I can say this is omega t, this is omega t, and this is omega t. And I can look at this as VAN. And this is VBN. And this is VCN. Okay. And after that, let me try to draw what is VAB as well. This is omega t. Okay. So let's try to divide this into 6 intervals. So this is 1, and I'm going to divide this into 3, and The same way, let me divide this also into 3. So I have divided this into 6 intervals. So I'm going to have 1, 2, 3 conducting here, what I had shown here. So I'm going to have VA and VB having 1 by 3 VDC. So this is 1 by 3 VDC. And this is also 1 by 3 VDC. Whereas this is going to be 2 by 3 VDC, but in the reverse direction. Please remember, from neutral, the current is going to flow in this direction. So neutral is at a higher potential. So I should show it as though this is 2 by 3 VDC. So this is 2 by 3 VDC. Whereas this is 1 by 3 VDC. This is also 1 by 3 VDC. And this corresponds to 1, 2, 3. The next one is going to be 2, 3, 4. And if it is 2, 3, 4, please note here 2 of them are positive devices, 1 and 3. Whereas here 2 of them are negative devices, which are 2 and 4. So I'm going to have them sharing. Actually 2 is corresponding to VC and 4 is corresponding to VA. Both of them are going to have minus 1 by 3 VDC. And VB, which is the only positive device corresponding to 3, that is going to have 2 by 3 VDC. So this is the combination corresponding to 2, 3, 4. Okay, so I can write this jumping up to 2 by 3 VDC, whereas this is going to come up to minus 1 by 3 VDC. Okay, so let me probably draw it like this. So this is minus 1 by 3 VDC and this is 2 by 3 VDC. After this, I'm going to have 3, 4, 5. Please note here 3 and 5 are going to share the positive voltage, whereas 4 is going to have the maximum negative voltage. So this is going to be like this, whereas from here it is going to jump like this. So if I try to draw the waveform, let me probably erase this because this is getting messy. So let me draw this somewhat like this. So I'm going to have, this is omega t. So I'm going to have first of all 1 by 3 VDC. From that it is coming to minus 1 by 3 VDC. Then it is coming to minus 2 by 3 VDC. Then it will come like this. So this is going to be the kind of waveform we get. The same way here I can draw VBN, what we got as 1 by 3 VDC here, that will go to 2 by 3 VDC, then again minus 1 by plus 1 by 3 VDC. So this will go like this. So this is going to be the kind of waveform we have. So if I try to look at what is VAB, so this is 1 by 3 VDC and this is also plus 1 by 3 VDC. So VAB will be 0 during this particular condition. So I'm going to have 1 by 3 VDC minus 1 by 3 VDC. So this is coming out to be 0. After that, I am having this as minus 1 by 3 VDC, whereas this is plus 2 by 3 VDC. So I'm going to have minus 1 by 3 VDC minus 2 by 3 VDC, from which I will have minus VDC. So this is going to jump to minus VDC. Okay. And if you look at the next one, I'm going to have minus 2 by 3 VDC here, whereas this is 1 by 3 VDC plus. So I'm going to have minus 2 by 3 VDC minus 1 by 3 VDC. So it will remain as minus VDC. So by extension, you should be able to draw this waveform somewhat like this. So the line voltage has plus VDC 0 and minus VDC as 3 levels. So here line voltage will have 3 levels, which are plus VDC, minus VDC and 0. Whereas phase voltage has 4 levels, which are 2 by 3 VDC, 1 by 3 VDC, then minus 1 by 3 VDC and minus 2 by 3 VDC. These are the 4 levels that we have got in 180-degree conduction and star connected mode. Okay. Now, we can definitely derive for delta connected mode as well. If I have delta connected load, how are we going to have the waveforms for 120-degree conduction and 180-degree conduction mode? I want you to derive this as homework. Okay, so please do this for delta connected mode in 120-degree conduction and 180-degree conduction modes. When the load is delta connected, what kind of line voltages and what kind of phase voltages we are going to have. I want you to derive this